Hi students, in this video we are going to discuss about Stokes theorem and terminal velocity. Now in previous video we discussed about viscous force. Now what is viscous force? It is the frictional force or opposing force that exists between various layers of a liquid when they are in relative motion. Now Stokes theorem, it gives the expression for the viscous force experienced by a spherical body which is falling through a viscous fluid. Okay, it gives the expression for viscous force experienced by a spherical body when it passes through a viscous fluid or any fluid. Now, how does the spherical body experience a viscous force? Imagine you have a beaker and a beaker is filled with a viscous fluid, for example castor oil or honey, and you put a very small spherical ball into it, like the ball bearing, you put it into the viscous fluid. What happens? Because of the weight of the ball bearing, it starts to move down. Now as it is moving down, the layer of the fluid which is in contact with the ball, the spherical ball, also starts to move, but the layer which is far away from the spherical body will be at rest. So there is a relative motion between the different layers, and this relative motion opposes the flow of the body coming down, or in a sense we can say that the spherical body will experience an amount of viscous force to its flow, and Stokes theorem gives the expression for this viscous force. According to Stokes theorem, the backward viscous force acting on a spherical body of radius small letter r moving through a viscous fluid of viscosity eta is given by the equation F is equal to 6 pi eta Rv. So, imagine we have a beaker which is filled with a viscous fluid and a small spherical ball or spherical body of radius small letter r is falling or moving through the fluid. Now as it is coming down, what happens? The layer of the liquid or the fluid which is in contact with the spherical body also starts to move down with the spherical body, whereas the layers which is far away will be at rest. So there is relative motion, and this relative motion opposes the flow of object coming down, the spherical body which is coming down. And according to Stokes theorem, the force, the viscous force experienced by the spherical body is given by 6 pi eta r into b, where r is the radius, b is the velocity with which the spherical body is moving, eta is the coefficient of viscosity of the fluid, and F is the viscous force. Now Stokes theorem is applicable mainly to spherical bodies. It is not applicable to bodies of different shape. Only if we can apply Stokes theorem to spherical bodies. Okay, that is the one condition. The next condition for Stokes theorem to be valid is the body which we are considering should be small, rigid and smooth, which means the size of the body, spherical body, must be very small and the surface should be smooth. There should be no irregularities, and it should be a rigid body. It should not be flexible. The second one is the fluid through which the body is moving should be homogeneous. Homogeneous means throughout the fluid its property should remain same. It is not in one region it is having a different property, in the other region that should be having different property. It should have same property throughout in the beaker or the container in which the fluid is taken. And the final one is there should be no slip between the body and the fluid, which means when the object or the spherical body is coming down, it should come directly, it should pass through each layer. There should be no slip or jumping or rotation or anything like that when the object is spherical body is coming down through the fluid. Only if these three conditions are, Stokes theorem is valid only if these conditions are there. It is applicable only to spherical body of very small size. The body should be smooth, really smooth, and small size. Third one, the medium or the fluid through which it is passing should be homogeneous, and final one, there should be no slip as it is coming down. Next topic which we are going to discuss in this video is terminal velocity. Terminal or final velocity. Now, what is terminal velocity, or how does the body attain terminal velocity? Now, imagine there is a spherical body, as I told you before, which is falling through a liquid. Okay. Now, as the spherical body is moving through the liquid, the body will be having a weight, and the weight will be acting downwards. And because of acceleration due to gravity, or because of gravity, what happens? As the spherical body is coming down, its velocity will start to increase, or we can say in a sense the body will start to accelerate. But there is, as I have told you, as the body is coming down, there will be viscous force acting on the body in the upward direction, which opposes its motion. So one thing that is viscous force. Second thing which acts in the opposite direction is buoyant force, or also known as the upthrust. This upthrust will also be acting in the opposite direction, that is in the upward direction. So weight of the body, the spherical body, is acting downwards, whereas viscous force will be acting in the upward direction, and also the buoyant force, the upthrust, will also be acting in the upward direction. So as the body is coming down, it is accelerating, but it also encounters opposing force from the fluid. And at a certain time, or at a certain point of time, we can say a stage is reached when weight of the spherical body is equal to, weight means the force experienced by the spherical body due to its weight will be equal to the sum of the upthrust force plus the viscous force. And if there is no force acting on a body, or if the net force acting on a body is equal to 0, then definitely what happens? The body will either be in a state of rest, or it will continue in a uniform motion. Since the body is coming down with a velocity, at that particular stage is reached where the weight of the spherical body, force experienced due to the weight of the spherical body, becomes equal to the upthrust and the sum of buoyant force. What happens? The body will start to move with a constant velocity. And this velocity is what we call the terminal velocity of the body. So, terminal velocity, the maximum constant velocity acquired by a body while falling through a viscous medium is called terminal velocity, and we denote it by the letter V suffix T, Vt. So the maximum velocity, constant velocity acquired by a body while falling through a viscous fluid is what we call a terminal velocity. So now let us derive the expression for terminal velocity. For that, we consider a viscous fluid and a small body, a spherical body of mass m is starting to fall or moving through the spherical body, and because of the weight which is acting downward, the body starts to accelerate. Now, as the body is coming down, it is accelerating, its velocity is increasing. At the same time, viscous force is acting in the upward direction, and the upthrust or buoyant force is acting in the upward direction will try to oppose the motion. So, velocity attained by the body after an interval of time. Okay, for this, consider a body of mass m, radius r, and density rho flowing through the liquid. Now usually we take rho, density rho, as the density of fluids, but in this expression, in this derivation, we are taking rho as the density of the spherical body falling through the viscous liquid. Okay, and let sigma be the density of the fluid. Sigma, density of the fluid. Don't get confused. Rho is the density of the spherical body. Sigma is the density of the fluid through which the body is falling down. The various force acting on the body are, which are the various forces? First one, force due to weight of the body, spherical body, acting in which direction? Acting in downward direction. And is given by F is equal to M into G. Now, we are going to convert mass in terms of density and volume. We know density is equal to what? Mass by volume, or mass is equal to density into volume. And for a spherical body, the volume is 4 by 3 pi r cube into rho, which gives the mass. So this equation can be written as F is equal to 4 by 3 pi r cube rho G. Equation 1. Okay. Next, the force which are acting in the upward direction. Second force is the viscous force acting in upward direction, and is given by F is equal to, according to the Stokes theorem, it is F is equal to 6 pi eta RV. Now the third force which is acting on the body is upthrust. It's also known as the buoyant force, acting in which direction? In upward direction. We have studied in 9th standard that whenever body is immersed in a liquid, they experience an upward force known as the buoyant force. And this force is equal to what? Is equal to the weight of the liquid displaced by the body. So F is equal to weight, again it is mg, but in this case this is a liquid being displaced, so we write 4 by 3 pi r cube into density of what? Density of the liquid into G. Okay. Now, what is the next step? Next step is, at the stage is reached when the force, downward force, become equal to upward force and this body start to move with a constant velocity. When weight, force due to weight is equal to upthrust plus this upthrust force plus viscous force, what happens? The body attains constant velocity. So we can write 4 by 3 pi r cube rho G is equal to 4 by 3 pi r cube sigma G plus 6 pi eta r V. In our case, V is the terminal velocity, so we are denoting it by Vt. Okay, or you can write 6 pi eta r Vt is equal to 4 by 3 pi r cube G into, you bring this term opposite side, you will get rho minus sigma. Now our aim is to find out what? Our aim is to find out what is the terminal velocity Vt. So we can write, cancel the common terms, you bring the 6 to the side, you will get Vt is equal to 2 by 9n r square g minus sigma whole divided by eta. So the expression for terminal velocity is Vt is equal to 2 by 9n into r square rho minus sigma into g the whole divided by eta. Now this is the expression for terminal velocity attained by a body which is moving through a viscous fluid. Now, if you look into this equation, it is clear that V, T, terminal velocity is proportional to the radius square of radius of the body. That is, terminal velocity will increase if the radius of the body is also increasing. A very simple example is that of the raindrops. Now imagine it is raining and initially the size of the raindrops will be very small. Now as it is coming down, it will be coming with a very small velocity. But as bigger drops are coming down, what happens? The velocity is also increasing. So terminal velocity increases with the radius of the body. Next, terminal velocity is proportional to the difference in density of the body and the fluid. If density of the body is greater than density of the fluid, what happens? Terminal velocity will be positive and the object or the body will be coming down. But if the density of the body is less than density of the fluid, you know what will happen? Definitely it will come up, because terminal velocity will be negative according to the equation. Rho minus sigma Vt will be, or terminal velocity will be negative and the object will be coming up. And if density of the body, that is object, is equal to density of the fluid, what happens? Terminal velocity will be equal to 0, which means the body will come to rest. It won't come down or it won't be moving. And also it is found that terminal velocity is proportional to coefficient of viscosity. I hope this video is clear to you. Thank you.